I think I've got some good memes for this week, you guys. Um, so why be thinner when you can have more dinner? Yeah. And then it's also a cat, so that makes it 10 times better. One day I hope to be wealthy enough to not do a double take every time I see abandoned furniture on the side of the road. I honestly still do this. Too many years of being a poor college student really get to you. uh, I don't know if anyone else. I used to live at Beverly Apartments, and when people moved out, like the stuff you would find at the dumpsters, you guys. Yeah, I found whole dressers. Like, obviously, you wash it and you don't take anything that was in the dumpster. But yeah, Beverly and Park. Woo! There is so much treasure out there, you guys. It's crazy. Actually, this dresser I have behind me came from the dumpster out there. So, you keep it, it works. Yeah, flat screen. You never know. It's nuts. Um, okay. And then the last one, please nobody get me fired over this. It's slightly inappropriate, but I like thought it was hilarious. So, dolphins having sex, meet famous poets, and you get E.E. Cummings. And then I just like the comment at the bottom. Anyways, we're all adults. Hopefully that didn't offend anybody, but I thought it was hilarious. Okay. What are we talking about today? So we're doing chapters 8 and 9, quickly progressing through our little textbook that nobody is required to read. But we're talking about correlations and regressions, and I put this cat here because I figure that's what most of you feel like at this point in the semester, because midterm season has relatively passed over, or maybe it's still going for some of you. Maybe it never ends. But this is relatable. And also, it's relatable because we're talking about correlations. Oh, I have jokes too. Yeah. Anyways, so correlations and regressions. If we look at our flowchart, this is where we are. We have a parametric dependent variable, and then we also have a parametric independent variable. So generally for our class, this means that we have ratio data for both the dependent and independent variable, or variables, right? We can actually have multiple variables for this week as far as independent variables are concerned, which we will get into. But if both your independent and dependent variables are parametric or ratio for the most part in our case, that means we want to run a regression or correlation. So we're going to talk about correlations first because they do help make the regressions make more sense. Because regressions are built off of correlations. And I feel like most everybody, by the time you get into this class, have been exposed to correlations before. So what are they? Basically, we're looking at the relationship between two variables, right? Meaning we're looking at the relationship between an independent variable and a dependent variable, which we call a bivariate correlation. We could also look at a correlation or relationship between 3 or more variables. So that's what I was saying. We have more variables entering our statistics sphere. But we can have 2 independent variables and 1 dependent variable, or more than 2 if we're getting fancy. And we call that a multiple correlation. The one thing to note is that in both of these examples, we always only have 1 dependent variable. Okay. And that'll be true for regressions as well. For good reason, but 1 dependent variable, but any number of independent variables. Okay. Also, if we have 3 or more variables, we can find partial correlations, which basically look at the relationship between 2 variables without a third factor kind of contributing to that relationship. So we don't really go over partial correlations in this class just because we don't use them for any of our calculations. So bivariate and multiple are going to be the ones that we focus on.
Natalie,
Yeah.
for the multiple, could you assume then that the on the activity that we did this week, could you assume that the dance intervention, since there was two like actual measurements, would that be technically multiple, or do you still count that as one independent variable?
Uh, so the intervention itself was one independent variable, but it had two levels.
Gotcha.
Yeah.
Thank you.
Uh-huh. Okay, so correlations. In our class, we use Pearson's product moment correlation coefficients. That's a mouthful. But there are other types of correlations. They just have different assumptions and rank things sometimes by strength. So Pearson's correlations are the most commonly used one, probably the one that you've been exposed to in other classes before, and we denote the correlation using the letter R, which may sound familiar. But R, or the value of R, can range anywhere from -1 to +1. And the value 1 represents a perfect correlation. So +1 would be a positive correlation, -1, negative correlation. So if you think about, we'll look at some graphical representations, but usually we associate a positive correlation with a positive slope, right? Especially if it's a linear relationship. Negative correlation, we have a negative slope. So the halfway point between those two is 0. And when the slope is undefined, that means we have no relationship. Okay. One thing to remember is that the numerical value and the sign mean two different things. Okay, so the numerical size, right, the value, anything between -1 and +1, is going to determine the strength of the correlation. Okay, so numerical value. So if we had like 0.5, that would indicate a certain type of strength, right, versus 0.3 or whatever. The sign of the correlation coefficient just represents the direction of the relationship, right? So if it's positive or if it's negative, okay? The sign has nothing to do, like a correlation of -0.4 is not less than a positive correlation of 0.4. They're equal strengths, they just go in different directions, okay? So the sign is the direction, value is the actual strength of the correlation. We would use correlations when we want to establish unknown relationships. We might also be validating known relationships from the literature. So if someone's already done something and you're just trying to confirm that and expand upon it, that's cool too. Okay, so establishing relationships is the goal of a correlation. Sometimes we can use correlations to validate different protocols and equipment to see how accurately, like if we were doing like body composition measurements and we wanted to see how closely our skin fold and bioelectrical impedance, do they actually produce the same values, or is there a lot of deviation between the values if they're supposed to be measuring the same thing? So we can use correlations to compare different pieces of equipment. And then we can also, I put this in here as a side note for your activity. So hint, hint. We can see how well a test predicts performance. I do want to make a clarification. We're not seeing if we're not predicting performance specifically. So regressions, we'll come back to this later. Regressions are able to predict a dependent variable. We can use correlations, however, on a real data set and compare it to a regression analysis and then see what the correlation is between the predicted values and the actual values to see if our prediction equation worked. So that's a method we call cross-validation. So we can use correlations in cross-validation data sets to see how much or how good our regression equation actually works on our data. Okay, but like I said, we'll come back to this. And you have an example in your activity this week. So most of the time, people hate that part of it, but yeah, it's fun. Last major thing I want to point out when we use correlations is that correlations do not prove causation. This may be a familiar phrase to some of you. And what do we mean? We're going to have a small segue to explain this. Okay. So correlations define relationships. Usually when we talk about causation, we're meaning cause and effect. So you have some type of experimental intervention. What is the effect of that intervention? That's what causation is referring to. Okay. So I like to use the example of having an independent variable of IQ and a dependent variable of GPA. Okay. We want to see how does a person's IQ relate to their GPA. Some people might say, oh, the higher IQ you have, the higher your GPA, which, I mean, it could be true, it may not be. I don't know. Okay. But saying that having an IQ causes a person to have a high GPA is not the best statement to use. Okay. And reason is, right, we can say that there is a relationship between these two, but we also have factors like motivation, study habits, financial support, study time, instructor, parental pressure if you know, like still have your parents on your backs about school, right? So saying that something is related is fine, but saying that a correlation or the values that you get from a correlation mean that somebody is going to have a certain outcome is not the best wording. Okay, so correlations don't prove causation, they just indicate that there's a relationship. And the nice thing is that usually we can go both ways. So I could say, oh, is GPA a factor for IQ, right? Usually the relationship you can compare in either direction. Cause and effect, you cannot. So if we use the example of leg length and pant length, typically we say that these two things would be related. The longer legs you have, the longer your pants should be, right? But we can't say that having leg length or longer legs will cause you to have longer pants, right? Because typically they would go both directions, right? So we could also say that usually people with longer pants are generally expected to have longer legs, right? But we can't say that having long pants is going to cause people to have long legs. Like you can't make your legs stretch or grow. So using the word cause in a relationship situation, we don't do that. Okay. We can say a relationship exists, but that's it. That's as far as we can go with correlations. Okay. Let's go to our graphical representations. So scatter plots are typically used when we have correlations, and we've already looked at these, you guys. Remember I asked you questions in previous activities that was like, which of these do you think are related to each other? Okay, so you intuitively already knew what correlations were just based on looking at the pattern that emerges. But what do these numbers actually mean? Okay, when we actually get a correlation coefficient. So we said 1 is perfect, right? And that's when the change in x is proportional to the change in y. Yes, we are going back to high school algebra, and we're going to be dealing with equations of the line. So I hope you remember your y equals mx plus b. I hate to mess with your brains, but we're actually going to change the variables in it. They mean the same thing, but they're just in a different order. Okay. But this is a perfect correlation, right? Change in x is the same as the change in y. And as the deviations between the change in x and change in y grow, you can see that our line gets looser and looser and looser, or the dots get further apart. And that indicates that the relationship is weakening. Okay, so with positive values, our slope is positive. Okay, and usually we say anywhere between 1 and 0.7 is strong, between 0.7 and 0.3 is moderate, and 0.3 to 0 is weak. Okay, 0, you're being equal to 0, meaning no relationship at all. Okay. The same strengths go for a negative correlation. Okay. So just one thing to note, for a positive correlation, right, it means that as one variable is increasing, the other one is increasing. Negative correlation is the opposite. As my x variable increases, my y variable is decreasing. Okay, so negative change in y over a positive change in x gives us a negative value. Okay, so perfect negative correlation, right, would be a 1-to-1 change in each variable. But then we get the same strengths as we had in the previous slide. So any values between 0.1 and 0.7 are strong, between 0.7 and 0.3 are moderate, between 0.3 and 0 are weak, right? So the actual numerical value indicates the strength, the sign indicates the direction. Any questions? Doing okay? Cool. And then, as I previously said, a slope of 0 would mean no relationship. Okay. So now that we've seen dots, right, in our scatter plots, which are our most commonly used visualization, we can start to look at the line of best fit. So you could see that generally there's trends, right? The stronger the relationship, the more defined the trend is. And I think some of you have added trend lines. I didn't ask for them, but some of you have added trend lines in your graphs before. And trend lines in Excel are the line of best fit, or the best fit line. Okay, so what this line represents is the best linear estimate of the relationship, right? And that the strength of the actual value that goes with the slope is going to change the tilt of the line, right? So if it's a positive, the closer that r value is to 1, the more that we will have this 1-to-1 line relationship. It'll never go above this, okay? At least not in our situation for our class. Because 1-to-1 is as good as it gets. But the weaker it is, the more horizontal the line will become. And then the same thing with negative, right? Perfect 1-to-1 is as good as it gets. No correlation would just mean that everything's all over the place. So how do we get this line? Good question, Natalie. Let's look at this formula. Okay. So this R is a simple formula for calculating R. We're lucky, we don't need to know this, but I conceptually walk you guys through it to show how we get where we do. SPSS will calculate this for you. You can also easily calculate it in Excel, which I'm pretty sure I give an example of. So you don't need to know like any formulas for R. But conceptually, it's good to know that we're looking at the summation. So we have a data set of X number of people who have an X variable measurement and a Y variable measurement. If you remember way back to the first week of school, we said that X variables represent independent variables, Y variables are dependent variables. Okay, so we have measurements for 2 different variables that have been on this, they're measured on the same person. So they're a paired set of scores, right? we can look at the deviation of each score from the mean of our sample, which we know we can define as z-scores if we can assume we have a normally distributed sample, which hopefully we do, okay? So using these z-scores, remember those indicate the distance from the mean, or the deviation from the mean, and the correlation is going to be looking at the direction and the size of deviation from the mean. So we know z-scores can be both positive and negative, and they represent deviation. Correlations are just looking at how much does each variable deviate compared to the other. So if we use this concept of z-scores and deviations, we can create this little example, okay? So let's say that I have my x variable on the horizontal axis and my y variable on the vertical axis. And I have some mean when I put all of my x variables together. I have a mean when I put all of my y variables together, okay? I can pick, oh, and they intersect at the center of the line. But we know that for each variable, we're going to have above and below the mean, right? So negative z-scores on this side, positive z-scores on this side. And then we have the same thing for the y-axis, right? With our negative values kind of converging towards the origin. So if I pick a point on this scatter plot, I chose this one. Okay, that was pretty obvious because it was the only circle that popped up. I can look at the change in x minus the change in y. And if I put it into that equation that I showed you on the other page, we end up getting the sign of our value, okay? So if I chose this value down here, it's going to have a negative z-score based on its relationship to my mean of my x variable, okay? So it exists a negative distance or a negative z-score distance from the mean of my x. I also have a negative z in my y direction, okay? So that would represent, right, a negative direction from the mean of the y variables. If I do negative z times negative z, I get a positive value. Okay, so a point underneath the line, or below the means, not underneath the line, a point that's below both of the means for each of the variables is going to have negative z-scores. Two negatives times each other give you a positive, okay? If we go above the means, right, say we're picking this value, that would correspond to a positive z-score in the x direction and a positive z-score in the y direction. So two positives times each other give us a positive r. Basically what we do in a big correlation equation, which we don't talk about in this class because it's overwhelming, basically what we're doing is we're saying for each of these points, we're going to sum up what the difference is between them, or what the deviations are between them and this line of best fit, and we're going to see what the strength of the relationship is, right? So if we have very, very small deviations both above and below the means of each of our variables, those are going to end up closing in on our line a lot narrower, right? And so in terms of the actual R value, the strength would be indicated by how closely each of these little dots is to the line, or how small of a deviation there actually is, okay? Which would give us more of a one-to-one comparison. And then the actual sign comes from the z directions for each point, okay? So we could also do this on a negative plot, same concept, where we have x variable, y variable, and their respective distributions. Okay, if I chose a point down here, that's associated with a positive z-score in the x direction, but a negative z-score in the y direction. So if I do positive x times negative y, I get a negative r value, right? And then if I did a value above, above the y mean but below the x mean, so I would take this value up here, right? I have a negative z in the x direction, but a positive y, or positive z in the y direction. Multiply a positive times a negative, and I get a negative r. Right? So again, we figure out the sign by kind of looking at all of these deviations put together. And that will end up telling us what the slope or the sign of our slope is. Okay. Any questions on that? Cool. All right. So thank you, SPSS, for doing good things for us, and Excel. But now we have to talk about the coefficient of determination. So this is also an important part that comes in. I think it bears a little bit more significance when we talk about regressions, but it's still important when we talk about individual relationships. So the coefficient of determination is synonymous with the word covariance. So you can use both of those interchangeably to refer to exactly the same thing. Okay, and we represent covariance or coefficient of determination by r squared. And what r squared is going to represent is the shared variance between two variables. Okay, so we know how to calculate r. If you just square that value, you can actually present it as a percentage. Okay, so if I had a correlation coefficient of 0.7 and I found the coefficient of determination by squaring, I would get a value of 0.49. I can turn this value into a percentage and say that 40% of the variability that I see in my dependent variable is explained by the independent variable. Okay, so if we use the IQ and GPA example, where IQ is my independent variable and GPA is my dependent variable, let's say that the relationship between those two things is 0.7, right? My coefficient of determination, or my covariance, would say that 49% of the variance we see in GPA is explained by IQ. Okay, just to use actual examples of variables. The rest of the percentage, so 100% minus 49 should give us 51, right? Whatever is not explained by the given independent variable that you've chosen means that the rest of the probability is due to other relationships with other factors or other variables. So when I put in like study time and who's the instructor and what's your financial aid or etc., right? If IQ didn't completely explain GPA, that means percentages from other factors could be contributing to GPA. So that's what this r squared means. How much shared variance do we have between the two variables?
Hey, Natalie. Mm-hmm. How much error is in this coefficient of determination? Would it be minimal error because you're accounting for the rest coming from chance or other factors?
Are you asking like what the significance of it is?
Yeah, like how much error would be in that 49% of that variability?
It depends. Yeah, so we actually look at the error when we get to the regressions. And usually we determine how much error exists based off of how a given variable contributes to a regression equation. For correlation coefficients, or when we're just dealing with like bivariate or multiple correlations, we only get p-values for the r. We don't get p-values for the r squared. Gotcha. So usually you can determine if your r squared is significant based on if your r is significant, if that makes sense.
Yeah, thank you.
Yeah. So the percentage that is explained for the shared variance is your coefficient of determination. The rest that's due to other relationships or some chance or error is your coefficient of non-determination. And the way we figure that out is just 100 minus whatever the percentage you got for r squared was. Okay. So if you're a visual person, we can use Venn diagrams to represent the concept of covariance. Let's say we have variable A and B, right? Maybe A is our dependent variable and B is our independent variable, right? Covariance just represents, right, how much overlap is between these two variables, okay? So if we have 0 overlap, that would mean that we have no relationship or no shared variance, right? So you can kind of see how the correlation coefficient plays into this covariance explanation, right? So no overlap means no relationship, 0% shared variance. However, if we have a total overlap, that means we likely have a very, very strong correlation or strong R, right? If we perfectly overlap, that means our R is either +1 or -1, and our shared variance would be 100%, meaning that all of variable B explains the outcomes that we see in variable A. Okay, but the degree of overlap will represent your covariance. So if you like circle visual representations, you can think about Venn diagrams. All right, that's kind of the conceptual stuff, or the conceptual foundation behind correlations. Now we need to go through assumptions, because this is going to be a section. I try to drill this into you guys when we do our activities, but and the reviews as well. But it's good to start thinking about these because assumptions are necessary for any statistical test, but they are different for every statistical test. So that gets fun. There's 2 main assumptions you have to have for every single test. That is random sampling and a normal distribution. Both of those 2 things make sure that you have a representative or a sample that's representative of the population, which is the whole reason we do statistics in the first place. And that was the whole topic of last week's lecture, is how do we take a sample, do some stuff to the sample, and then kind of announce the generalizability of that sample on the population. Okay, so random sampling and having normally distributed data are usually always the 2 things that you have to have for any test that we run in this class. So to just put those in your head, and when you see assumptions, just think those 2 things need to be listed. There's more specific assumptions for different tests that we do. So for both bivariate and multiple correlations, for our class, we do the Pearson's correlation coefficient, right? So you're going to need both parametric and dependent variables for those calculations to work. Okay, I already mentioned normal distribution, no outliers, bad, but okay. And then you also need to be able to assume that you have a linear relationship. Okay, so that means we can create a line of best fit on our data and it doesn't look kind of crazy. Okay, there are such things as curvilinear relationships or exponential relationships that you may have been previously exposed to. We would not be able to apply those types of relationships with the Pearson correlation coefficient. Okay, so the relationship needs to be linear, which is usually why we use scatter plots, because visually we can see if there's a curve in the data or if it's pretty straight. Okay. So these are kind of the 4 things you want to keep in mind when you're looking at a correlation. For the null hypothesis, and this is also a good idea, start making a list of assumptions and start making a list of null hypotheses, because we like to get crazy with null hypotheses in this class. And it's important to know the null hypothesis because that's the one that's statistically tested, right? And for all of our null hypotheses in this class, we're going to use a two-tailed test, aka a non-directional hypothesis. So we can have differences above or below the mean. Okay. The primary research question, or the format of the research question that you might see, is that somebody is investigating if there is a significant relationship between 2 variables. Okay, I feel like that's pretty self-explanatory after what we talked about on what correlations measure. But the non-directional hypotheses for a bivariate correlation, again, I put the null in yellow because that's the one you actually have to know, right? Null hypothesis for a correlation would just say that there's no significant relationship between the independent and the dependent variable. Okay. The research hypothesis is mutually exclusive to that. So if null says there's no relationship, the research hypothesis will say that there is a significant relationship. This one's nice and easy, just laid out there for you, okay? We can also represent this as a baby equation using our correlation coefficient and some values, right? So a two-tailed hypothesis, we could also say that R is equal to 0, right? Because we know that the value of 0 indicates that there's no correlation. Alternatively, anything that is not 0 would represent the research hypothesis. And we can determine significance by saying, like, this is our level of confidence, this is the alpha that we are accepting for this particular test, and then we can calculate a p-value for R to see if the relationship is significant or not. And sometimes we can say we have a significant weak, we have a significant moderate, or we have a significantly strong. So significance can be proved for any strength of the correlation, which is why I put this part in red, that P indicates the significance, not the strength, right? So the actual value of R represents the strength, sign represents direction. The p-value for R just tells us if the relationship is significant or not. Okay. Any questions on bivariate correlations?
Can you repeat that one more time? So P is whether it's significant or not, R is the strength, and then the positive negative is which direction?
Correct.
All right.
Yes. Okay. So far we've just been talking about we have 2 variables, one independent, one dependent. We can do correlation coefficients when we have multiple variables. So that's where we get the multiple correlation, right? So in a bivariate correlation, right, we found the coefficient of determination or the covariance, and we said that if we squared R, we got some probability that explained a given dependent variable. And the rest of that probability or the rest of that percentage meant that there's potentially other factors that are contributing to the outcome of the dependent variable. So that's where multiple correlations come in handy. And we can calculate R for the relationships between multiple independent variables on a given dependent variable. Okay. The book likes to note that the multiple correlation coefficient is a big R. In SPSS, it doesn't matter. Okay. So SPSS, you'll just see a little r. Anytime you see r, just think, oh, it's a correlation. Okay. But the only difference between a bivariate and a multiple is that you have more independent variables or more x variables, okay? And we can also calculate a coefficient of determination by just squaring r. Technically, the interpretation of the r squared means exactly the same thing, okay? So for a multiple correlation, we end up changing the null hypothesis a little bit. Usually for multiple correlation, and I'll show this example, the outcome we get just gives us a bunch of bivariate correlations, okay? But generally the research question would say, I think that there is a significant relationship, or maybe not, right, between X number of independent variables and a certain dependent variable. So again, if we're using non-directional hypotheses, the null hypothesis will say no significant relationship, meaning that R is equal to 0. And the research hypothesis would say that there is a significant relationship, meaning R is not equal to 0. So technically, the hypotheses for correlations are exactly the same, multiple and bivariate. One, we just have plural independent variables, that's all. So what you'll get practice with in the activity this week is creating a correlation matrix. And I make you create one before you put stuff into SPSS. That way you understand how it's set up. So if you have the PowerPoint version of the notes, in the notes section, I only have one slide of these. In my PowerPoint version, I have 3, but all of these notes on the bottom are actually in the notes section in the PowerPoint version. So if you're working off the PDF version, just know that these words are still available to you somewhere on Beachboard. So this is a correlation matrix, and this is usually what we're going to build when we run a multiple correlation. Or if we have a bunch of variables. So let's say that I wanted my dependent variable to be isokinetic torque. And I have fat, BMI, weight, height, fat-free weight, and age all as independent variables. I can assign or run a bivariate correlation between isokinetic torque and each of these variables and get a single R value. Or I can just say, SPSS, I want the relationship between all of these variables, which we call a multiple correlation, and it spits out a bunch of little bivariate correlations in this cool matrix. So it's pretty much like reading a map. So isokinetic torque and age has a correlation coefficient of 0.876, which would be a strong relationship, meaning the older you are, the greater isokinetic torque you have. I think these numbers could potentially be arbitrary. I think they were presented in the book. I didn't make them up myself, but I don't even know if they're real or not. But you can look at all of these different relationships, and that's really cool. The note I have down here is that the right half of the matrix is usually empty. For the ones that we create, we'll keep it empty. SPSS, I think, gives you both the top of the matrix and the bottom of the matrix. Totally up to you which side you read. But wherever you see this diagonal line of 1s in your matrix is going to indicate the divide between the top and the bottom. And usually we just make 1/2 of the matrix because all of the values that would be on the upper side of the matrix are exactly the same as down here. So if we were looking at the relationship between height and age, this value here that would be here is the same as what is here, if that makes sense. Okay, so the top is redundant with the bottom, why we only look at one side. Another note is that all of these values along the diagonal technically don't count when you read your matrix, because we know that if we took a set of ages that we've collected on people and matched them with the same set of ages, obviously we're going to get a one-to-one. Okay, so when you're reporting any information on your correlation coefficients in your activity, don't mention the perfect correlations. That's kind of a given. We know that they're perfect. Okay. And then the last thing, the bottom row or the first column, depends on how you insert your variables. But usually the bottom row, in the way that I typically like to set my stuff up, will display all of the bivariate correlations between an independent variable and a dependent variable. Okay. But you can also think of it that the first column could also do the same thing if you decided that you wanted to organize your stuff in that way.
Now I have a question.
Yeah.
Would the I guess left column, would that be your independent variable, and the top one, would that be all your dependent variables? I mean, I know they're all the same, but I'm just kind of curious.
Yes. So if I chose isokinetic torque as my dependent variable, all of these across the top minus the isokinetic torque would be dependent variables.
Got it.
Or independent variables, sorry.
Oh, okay, so the top's independent, and I guess the horizontals, or vertical would be the dependent.
It kind of depends. So
Okay.
the one variable that has all of its row filled in could be considered your dependent variable. And everything that it crosses with is an independent variable.
Got it.
Right? But you could also organize your matrix so that your dependent variable is in the first column, in which case every row that it pairs with would be your independent variable. So it just depends on how you want to organize your variables. Sometimes it matters, sometimes it doesn't. So in a regression, it matters. So just know that the first column or the last row will usually be attached with your dependent variable. Because when we run regressions, you also get a correlation matrix. But yeah, two different ways to read it. And then in SPSS, you'll usually get a correlation matrix. I have a simple one that's been created that looked at the differences between height and jump distance. So you can see our perfect correlations run across the diagonal. And then this is how it's set up in the SPSS output. So the Pearson correlation is going to give you your R value. That should make sense, right? So this one's saying that we have a 0.706 R, which is a strong positive relationship based on what we said our values indicate. And then anytime you see sig, that's indicating significance, right? Or P, okay? So this is the P value, the actual calculated P value that is attached to this correlation coefficient. So we know it's a strong positive correlation, and we also have a significant correlation, right? But this P value is always compared to the alpha level that you set. So if we ran this, if we ran this correlation with a confidence level of 95%, our alpha would be 0.05. And then we would say, is P less than or greater than 0.05? In our case, it's less than 0.05, therefore we have significance, okay? Usually at the bottom of the table, it'll give you 1 asterisk or 2 asterisks, and it'll tell you correlation is significant with some alpha level. So sometimes it'll say 0.01, sometimes it'll say 0.05. Usually you set your level of confidence before you do your test. So it'll automatically mark significance, but it will say, oh, if you happen to choose a 99% level of confidence, that would give you a 1% chance of error. This is also what would be significant. So those little notes at the bottom are kind of just extra. Okay. But does anybody have questions on correlations in general? Cool. I was hoping people wouldn't get intimidated by a lot of slides because it's mostly pictures. But now we're going to talk about regressions, which the conversation from correlation to regression should flow pretty nicely because correlations are used in regressions. The only difference is how we describe the use of the test. So we're still dealing with a parametric independent variable and a parametric dependent variable. The numbers of variables can change, either bivariate or multiple, but our goal of the test is what's different. So in a regression, usually identifying the dependent variable is a lot more important than identifying a dependent variable in a correlation. A lot of times correlations, people don't even identify which is their dependent, which is their independent. In a regression, it's important that you indicate which one is which, okay? So regressions are used when we want to predict the value of the dependent variable based on its relationship with independent variables, or an independent variable if we've only got one, okay? So when you see a regression, think prediction, okay? This is that word, prediction, and there's another word that I commonly use in questions when I want you to do a regression. It's not coming to mind right now. Anyways, predictions, regressions. Connect those two words together, okay? So the goal with a regression is to create a linear equation, right? So we're expanding off of linear correlations or linear relationships to build an equation that's going to help us predict a dependent variable using relationships with independent variables. So we can have two types of regressions, bivariate and multiple. The characteristics of how we get the word bivariate and multiple are exactly the same as correlations, which is super convenient for all of us. The assumptions of a regression, however, change. You're still going to adopt the same assumptions that you have with correlations. So we still need random sampling. We still need to have our certain variable characteristics, and we still need a normal distribution. And we still need a linear relationship, okay? So we take all of the assumptions from a correlation and plop them into a regression. And then we add two. The first one is multicollinearity. We don't want any of it, okay? So no multicollinearity, and I'll explain what that is on the next slide. And then we also want homoscedasticity. It's the worst word to say, and I can never say it. Basically, if a scatter plot is homoscedastic, anyways, that word, yes, homoscedastic. There we go, got it, okay? If it's homoscedastic, that means that the variance of the residuals does not vary along the regression line. I give visual examples of what residuals are in a couple of slides. And I'll show an example of what it looks like in a real data set. But basically, if you don't have a homoscedastic distribution, it's considered heteroscedastic. So that's going to be a fanning pattern. And typically we want to control for this so that we don't inflate the chances of getting a type 1 error. Okay, so let's go through these two individually. So multicollinearity is going to happen when you have two independent variables that are strongly correlated with each other. Okay, or they could also be, it could be multiple, right, two or more. Okay, so this could arise from variables that are usually kind of built into calculations of other variables. So I've given the example of what if we looked at the relationship of certain variables and how they predict body fat composition. And I included mass, and fat-free mass. All of those kind of contribute to each other, right? So fat mass could also contribute to mass. Fat-free mass could contribute to mass. So if we can define super strong relationships between each of these variables, that could be an issue with multicollinearity, okay? So kind of if you break the word down, multi means multiple variables. Like coexist, right? Or these two things have some relationship, and that's indicating a linear relationship. So multicollinearity is when you have two or more variables that are highly, highly related to each other. Another example I give is BMI versus height and mass, because we know height and mass are both used to calculate BMI. I actually give you guys an example in the activity this week of a data set that would have multicollinearity. We kind of ignore the fact because I don't make you guys test for this in this class, but you might notice that example without me actually saying it during the activity. A special case of multicollinearity is singularity, and that'll occur when you have a perfect correlation between two or more variables. Again, we do not want multicollinearity or its form of singularity. They're not good for our regression equations. It's okay if you're looking at a bivariate correlation, totally fine, but when you're predicting another variable, this is not a desirable thing to have. And we can test for this stuff in SPSS, but we don't do that in this class. So just the extent of these is knowing their definitions and knowing that they're in a multicollinearity, or having no multicollinearity is English is hard. No multicollinearity is an assumption of a regression for this class, okay? And then the last thing, or the last assumption that we added on from correlations, was I hate this word. You don't want heteroskedasticity. You guys can try saying it on your own, and I'm pretty sure you're just gonna have much of a tongue twister time as I do. But this is what it would look like. So we said it's a fanning effect, and you can see that the distance between the points down on this end of our distribution are closer to the line of best fit than the distances of points to the line on this end of the distribution. So that fanning effect is called heteroskedasticity, and it increases your chance of type 1 error. So it means it's not increasing the alpha level. Remember, that's set when you run your test, but the likelihood that you're going to reject the null when the null is true increases, okay? Okay, so how are you guys doing so far? You can use thumbs up, thumbs down. I will try to see what we're looking at. Thumbs up, mostly thumbs up. Okay, that's great. I haven't scared anybody. Maybe I have, and you're just not telling me. But hopefully we're okay. So regressions use the line of best fit as an estimation for y, meaning we use known relationships between independent variables and dependent variables to predict a dependent variable. Okay, remember, we're always predicting the dependent. So regression lines, we say, have a slope of b. When we look at correlations and we put a line of best fit in a correlation, the slope is r. Okay, and r is usually between -1 and +1. Similar concept of what the slope represents in a regression, but b is going to be in the units of whatever you're measuring. So it's not restricted to be between -1 and +1. B can generally be anything. And when we put a correlation into an equation, right, if we use that correlation coefficient and stick it into an equation, that value can also be in the units. So anytime you stick a slope in an equation, it can be in the units of the variable you're measuring. But I think that's important to note because some people are like, oh, B is the same thing as R, and technically it's not. R specifically has a certain range of values. B is virtually limitless in its value. Okay, but we said the goal of a regression is to build an equation for this line of best fit so that we can use these known relationships to estimate estimate. That's the word that I was looking for. Oh my God. Okay, so when I said regression, prediction, estimation is the other word that I wanted to verbalize but could not. So if you see estimation or prediction, just think regression. That was the other word. Yes, I knew it would come to me. It was literally right in front of me. Okay. All right, so we build equations. I'm sorry, I got really excited. We build equations, and we have to have two things in mind when we do this. We want to ensure that the sum of the residuals is 0. Okay, this equation doesn't really matter to you, but and you don't need to like memorize it. But what a residual is it's saying this model. We're looking at the y variable. So what is the actually measured dependent variable versus what is the dependent variable that the model gives us, or the equation. Model and equation are synonymous for regressions. So we're trying to make sure that the sum of all of our residuals is 0, or as close to 0 as possible. Right, so the residual is just looking at the vertical distance between the raw score and the line of best fit, right? So if we have a line of best fit going through our distribution, what is the distance from some actually observed score compared to what the model would say the score should be at a given level of X, okay? The other thing that we need to keep in mind when we build these equations is that we're minimizing the sum of squared residuals. And that is just saying in either direction above or below the mean. That's why we square. We kind of get the absolute, the absolute difference, the absolute residual. Yeah, we could probably say that. But that just tells us in general how much deviation do we have from the model. And the less and less deviation we have from the model, the better, because that means our model is pretty well predicting our y variable compared to what we actually observed. And that's the whole point. Make an equation that works. So what? Oh yeah, outliers have a big effect on the regression equation. For one, they can lead to this heteroscedastic effect, but also outliers just aren't good because they make things not representative of the population. So we always need to check for normality to get rid of those. But this is what I was saying. What? Put all of these terms into a visual representation. So we've got this X variable that is predicting a Y variable. And we can put a line of best fit through the center, which is our regression line. So we've got a couple important things on here. We'll get back to the regression line in a second. But the first thing I wanted to note is B sub 0. So you guys might be familiar. Y equals mx plus b is an equation of the line, where b is usually the y-intercept. M is the slope, x is representative of some variable. In SPSS, everything is b. And that's really jacks up your original idea of an equation of the line. So instead, we use subscripts to indicate what B is referring to. B sub 0 is the y-intercept. It is a constant. In SPSS, it'll actually be called constant. So don't forget to include this in your equation when you're building it. And I'll give you guys examples of how to build equations towards the end when we actually look at some SPSS examples, or output examples at least. Okay, so that's the first thing to note is B sub 0 is a constant in your equation. It's representative of your y-intercept, or where your line would cross the y-axis. The other thing is the regression line, or the line of best fit, has a slope of b. Excuse me. And usually, if we have multiple independent variables or multiple x variables, we would also add a subscript on b. So if we have like independent variable number 1, b sub 1 would represent the relationship of that independent variable with the dependent variable. If we had a second one in our equation, b sub 2 would be the relationship between independent variable 2 and the dependent variable. So we can keep building and building and building. But b generally represents the slope. B sub 0 is the y-intercept. Don't get those confused. And then the last thing is the residual. So all of these little red lines between these different points in the distribution and the line of best fit is what the residual is. So it's how much error do we have from the actual observed value to what the model would predict if we had a perfect relationship. Okay, so those are like the 3 main things you want to know about if you're looking at a regression line. Okay, so conceptual stuff is out of the way. Now let's apply it to a bivariate situation. Okay, so this is what the equation of a bivariate regression would look like. Very similar to your regular y equals mx plus b. Remember that b sub 0 is a constant, or the y-intercept. B sub 1 would be the slope of x, which is an independent variable. Okay, so all b is telling us is the rate of change, right? What is the output y? Because slope, remember, is rise over run, or the change in y over the change in x. So b is representing what is the change in our outcome or predicted variable y for every 1 unit change of x. Okay, because this is always, or most always, going to be some value in the units of measurement that you're working with. But it's not, remember, b is not the same as r, so that number can be anything numerically. Okay, so I like to use an example at this point just to like break up numbers and letters and stuff. So let me plug in and start sharing my screen. I like to use an example that applies to everybody. And I want to new share to iPad. Okay, so I like to use an example that applies to everybody, and that is college and how much college costs. So we can create a regression equation in which y is equal to the cost of college, or total tuition, if you will. And that's going to be our dependent variable, so we can write that in here as well. And our independent variable x maybe is the number of semesters that we attend. Okay, so I want to know Or if I wanted to look at a correlation, I could say, how are these two things related to each other? In which case, most of you would probably say, well, the more semesters you attend, the more expensive it is, right? We can use that relationship to predict the cost of college. So if we want to know what is the total cost, we can create some linear equation based on this linear relationship and say that, let's say the school charges you $500 to enter as a student. That's flat rate first semester. You only pay it one time. That would be like our B sub 0, right? So this is it's a constant. It's a flat rate. Doesn't matter when you enter college or not, or what year you're in, you had to pay this $500 to get in. Okay. And then we can say this is plus the cost of tuition. So usually if you're a full-time student, this ends up being about $4,000. crying, lots of tears. And then X is going to represent the number of semesters, right? Which we got from here. Okay, so 4,000 in this case is B sub 1, and we can say X is number of semesters, right? So I can predict how much college is going to cost based on how many semesters I plan on being in college, right? Because if I'm in college for a year, that means 2 semesters. 2 times 4,000 is 8,000, plus your base rate or constant of $500 to enter into the university. That ends up giving you your total cost. Okay, so this is the whole point of a regression, is to say, given a known relationship between two variables, how could I predict one of those variables, right? Given all of this other information in here. And that's all we're doing, okay? So this is essentially what the whole purpose of building a regression equation is for, or why we use regressions in the first place. And we're not just limited to one variable. We have multiple variables that we could implement into our equation. So we'll bring it back. First, before we skip on, that was just a segue to give you an example. The null hypothesis for a bivariate regression is going to be kind of what we've just explained, right? So the research question is going to say, how does variable whatever, right? And how does an independent variable predict a dependent variable, or what percentage? Sometimes we represent contributions in percentages, which we'll talk about in a second. But right, how well are we able to predict a dependent variable based on its relationship with an independent variable, or where we want to make a model so that we can apply this equation to other types of data sets. Okay, so when we look at a non-directional hypothesis, we would always argue the relationship, right? There's no significance. So in this case, the relationship between the independent and dependent variable, or the slope B that we end up getting from the regression model, that relationship is not significant enough to predict the dependent variable. That's what the null hypothesis would argue for a bivariate regression. The research hypothesis argues the absolute opposite of that, saying that the relationship does significantly help to predict the dependent variable. Okay. Any questions so far? Check-in time. I think we're doing okay. All right. So, how do we determine if a relationship is significant or not? This is where the fun begins. So, if you recall, when we looked at our example last week, the most basic example of statistical inference is saying how different or similar is a sample mean compared to the population mean or the population that's supposed to come from. So how different is a sample mean compared to an estimated population mean? And when we looked at that difference, we calculated standard error of the mean, meaning how far away is our sample mean from the population mean. Standard error is very similar to standard deviation, right? We just apply it sample to population instead of how far is a raw score from the sample mean. So we can do a similar thing with a regression, and we call it the standard error of the slope, or SEB, where B represents the slope for the regression line. You don't need to know this equation, just so you know. Usually if you're doing hand calculations, I give you the standard error for regressions, and then what's it called? SPSS will calculate this for you. So no need to worry about the calculation. But I think it is important to note that there are a certain degrees of freedom that are inserted into this equation, so that we have that sample to population jump, right? Without overestimating or assuming that our sample is the same as our population always. Okay, Y in this is just indicating what is the observed versus the predicted. And then we're just looking at deviations in X. So if you remember, we were looking at, I didn't show you the long equation, but correlations are looking at the deviation from a sample mean in both variables, right? And then we just see what is that combined deviation along some regression line. This is basically showing you the exact same thing, right? Or how much variance do we have in one variable, and does that variance match what we see in the other variable? Okay, if they line up, then woohoo, okay. But we have a standard error of the slope. That's how we translate our sample relationship into a population relationship. And then we can evaluate that relationship with a t-distribution. So we have a new table, t-table or t-distribution. It could be called both of those things. And what lies in this t-table are things called critical values. We will have lots of different examples of critical values. I actually took out the R table, which would have had critical values for correlation coefficients. Now you guys just have the T and the Z tables. The Z tables we'll get into 2 weeks from now. 2 weeks from now. But we'll stick with the t-distribution for now. And basically what this tells you is that given a certain degrees of freedom, which is usually based off of your sample size, based on that certain degrees of freedom and a certain level of confidence, the size of your relationship needs to be this big in order to be significant. That's what a critical value is. Just tells you how big does the difference need to be in order to be significant. So we can calculate a t-statistic, okay, which we just called t, to calculate the p-value for a slope of our regression. So technically we can calculate t and then compare it to the critical values to estimate our p-value. SPSS, I think you can run tests, but you have to get extra packages in Excel. But SPSS will give you the exact p-value for your t-statistic, or for the size of your difference, which is just saying how does the sample slope relate to what we would expect the slope to be in a population. So we can calculate this t from these 2 bits of information, and then we can compare that t to whatever the critical value is at a certain degrees of freedom and level of confidence. The rule of thumb is that if your statistic that you calculate is greater than the critical value, you have a significant regression line, or you have a significant slope of your regression line. If t is less than the critical value, no significant regression line, or no significant slope, no significant relationship. What am I talking about? Let's look at the table. I've put this on Beachboard for you guys so you can look at it. But I highlight that this is a t-distribution, and these are the rules to use the t-distribution for the regression, because the degrees of freedom is different for a regression than it is for a t-test, which we also use the t-table for. I love this class. It's not confusing at all. So you also might want to start making a list of what types of degrees of freedom and how to calculate those will change for each of the tests that we start to talk about in this class. I also summarize all of this stuff in the cheat sheet that's posted on Beachboard, so you can also take a look at that. I think that's in the study materials area, but I used a lot of headings, so it's easily navigable. But the degrees of freedom in our situation is n minus the number of independent variables that you have in a regression. So if we're doing a bivariate regression, the degrees of freedom should be just 1 as like the most basic. If we have a multiple regression, let's say we have 10 independent variables, our degrees of freedom, or sorry, not going to be 1. It'll just be 1 goes in this spot if you have 1 independent variable. My bad. Okay, so if we had 20 people and we had 1 independent variable, that would mean we have 19 degrees of freedom. Okay, if we had the same 20 people and we had 10 independent variables, that would mean that we have a degrees of freedom of 10, right? 20 minus 10. So that's how you figure out the degrees of freedom part. And then I like to look at the bottom. See these confidence levels down here? I like to look at those numbers instead of these up here, because some people get really confused where they're like 1 tail versus 2 tails. I don't know. 1 tails are remember when you have your hypothesis in one direction. So you're either saying, I expect to have only a positive relationship, versus I would only expect to have a negative relationship. So 2 tails would mean, it could go either way. But it's the alpha in your total tail. And so I think this confuses students up here. So just look at the confidence intervals. Most of the time we're going to be using examples with 90, 95, and 99%. You'll notice there's a 98%. You just kind of like glaze over that column. So 90, 95, and 99 are the ones that we focus on the most. But like I said, we can use this to estimate p-values. And the way that we do this is by comparing the alpha that would be associated with each of these 3 confidence levels. So if I had, let's say I determined that I had 20 degrees of freedom and I had a 95% level of confidence. The t that I calculate using that b divided by the standard error, that t is going to be compared to this critical value in this table. And this table tells me how, basically how strong my slope needs to be, or what value my slope needs to be compared to the standard error in order to be significant. So if the t that I calculate is greater than the critical value I've determined based on my sample characteristics and my level of confidence, then we can say that that slope is significant. Okay, so t greater than critical value, significant. T less than critical value, not significant. Okay. And again, in terms of significance, we're saying, is the slope of the regression, or is the relationship between our independent and dependent variables significant enough to actually predict the dependent variable? So that's that. We can also create confidence intervals, which you guys do need to know this equation. So remember, confidence intervals tell us where on the population would a certain characteristic be located based on our sample. So this should look kind of similar to the sample mean compared to an estimated population mean. So last week we had sample mean plus or minus a z-score times the standard error of the mean. This is pretty much the same thing. We're looking at where is the sample slope of our regression line plus or minus the critical value of t. Now, some students get this t confused with this t. Don't get your t's confused. Okay. This t is what you calculate. This is the actual difference that exists between your sample and your population, considering the slope b. The t that is in this calculation is the critical value that exists in the table at a given degrees of freedom at a given level of confidence. So that's why I put t sub CV at the bottom, so that you understand this t is representing a critical value that exists, right, at a certain degrees of freedom at a certain level of confidence. So that this TCV is going to come from the actual table. And then the standard error of the slope I usually give you guys. Okay. So this is what I wanted you guys to have some practice problems, calculating t, and then calculating confidence intervals so that you get practice discerning t versus TCV, but also knowing how they compare to each other if you're trying to estimate a p-value. So I have a video posted on that. If you want to work through these problems, these are the knowns. If you want to work through those problems to figure out things on your own, that's totally fine. And then you can watch the video, check your answers. If you want to watch the video as you go, also fine. Okay, but I would highly encourage you to do the practice problems because there usually is a question of some sort like this on the exam. Okay, so those are bivariate regressions. Does anyone have questions on bivariate regressions? Okay, using a known relationship to predict a dependent variable. We can expand bivariate regression by just adding more independent variables and calling it a multiple regression, which is usually more popular in scientific research, at least what I've come across so far. Usually if you're just going to be measuring a lot of stuff, you might as well look at relationships of lots of variables and try to build a regression equation. So you could see the framework of a bivariate regression still exists, right? Where b sub 0 is the y-intercept or the constant. And then we just tag on a known relationship between independent variable 1 and y, represented as b sub 1. A known relationship between independent variable 2 and y, which is b sub 2. We can go all the way until n, right, which is however many independent variables we have. But generally, the null hypothesis is going to be the same as a bivariate regression. We're just adding independent variables. Okay. So a non-directional hypothesis would say that the relationship between an independent variable, dependent variable is not significant enough to predict the dependent variable, right? And we have multiple independent variables. So a lot of times in research, what this will be worded as is like, if I was looking at Parkinson's disease state, or the severity of it. I could look at different gait parameters, such as like gait speed, or the amount of arm swing that a person has, or their stride length, right? Typically, people with Parkinson's are rigid in their movement and they can't take as long of a step. Typically, with arm swing, it goes away and gait speed decreases. So I can use all of these different variables to try to predict the disease state of Parkinson's, right? And in research, we would say arm swing, gait speed, and stride length are significant predictors of Parkinson's disease severity. Okay, so that's how you would typically see it in research, is that these independent variables are significant predictors of a dependent variable. That's another way that we can word the null hypothesis. Okay, independent variables are a null, no significant. I was just saying that's how you would see it in research. So the null of that would be that the independent variables are not significant predictors of a given dependent variable. The research hypothesis is usually the one that people say in the introduction of their paper, and that would say that we think these are significant predictors. Okay. But still the same concept as a bivariate regression, where you're saying, do these known relationships significantly predict a dependent variable that we've identified? Okay. So, check time. All right, 10 minutes? I can do it? Yeah, I think so. The variable priority, or how we create the regression equation, does matter. And the video that I don't think slide format is the best way to present the two types of methods that we use in this class. So I would highly recommend to watch the flowchart video, because that explains things way better than just reading words. The hierarchical method is like the simplest method, and in SPSS it's referred to as enter. That'll make sense when you actually interact with the program. But this just means that you, the investigator, has chosen the priority or the order in which your variables are inserted into your equation. Okay. Sometimes we do this if variables are some variables are easier to measure than others. If we already know that there's a stronger relationship between a certain type of measure or protocol with the dependent variable than there are with other measures or protocols. Or we just want to see what the difference is between different regression models, in which case we can manipulate the order in which variables are inserted into the model and then compare how that changes the outcome. So we'll use this one in activities just to see what the difference is between other methods. And one of the more popular methods that you'll see is a forward selection. So this is where we begin the regression equation with no independent variables in the equation. We're basically just starting with the constant, or the y-intercept. So you could also think it's synonymous of when x is equal to 0, there are no x's, okay? But the first step that we have with this forward selection is we insert the independent variable that has the highest bivariate correlation with the dependent variable. So whoever has the strongest relationship gets stuck into the model first. From there, we insert the independent variable that increases r squared the most. What's r squared, guys? Does someone want to say? I told you it would come back.
Something like the coefficient of regression or something like that?
Coefficient of determination.
Yeah, there you go.
Yeah, or the covariance, right? So now that we're inserting more variables, covariance means something to us now, right? Because we have who contributes to the relationship the most, and then who comes in after that, or who can add a greater percentage, because the whole point of this regression equation is to get the highest R squared possible, right? Because R squared means a shared variance between our independent variables and our dependent variable. The more or the higher the R squared is, the higher chance that we've predicted our entire dependent variable, or that we've accounted for the variance in our dependent variable. Okay, so it doesn't matter what method you choose, but typically forward and backward, you're maximizing R squared. Okay, or the shared variance between the independent variables and the dependent variable. So step 3, right, we've assessed, or we've stuck in who has the strongest relationship, who has the next strongest relationship, or who increases the covariance the most. If the increase of R squared, or the change in R squared, is significant, we keep that variable because we've significantly increased R squared, which is a good thing. That's what we want. If we do not significantly increase R squared, we chuck out the variable we just added. And then that's where the regression stops. Okay. Like I said, this makes a lot more sense with the flowchart. Backward elimination is just the opposite of forward selection. So instead of starting with no variables in the equation or the model, you start with all of the variables in the equation. And then you just remove one by one. And for forward selection, we said who has the strongest relationship, and strongest relationship and who increases R squared the most. Backward elimination, we say who decreases R squared the least, because we want to incrementally take away from R squared, okay, and say like who doesn't significantly contribute to this relationship. It's like a polyamorous relationship, like who does not contribute. Or it could be like roommates. Who doesn't wash the dishes? Just kick them out of the apartment if they don't wash the dishes, right? So we have everybody starting in the equation, and then we say who contributes the least to this relationship, and we kick it out. And then we see how does the R squared change when we kick that variable out. Okay, if R squared decreases significantly, then we say, oh, maybe that variable contributed to the equation a little bit more than we thought it did. So we keep it in the equation, and then we kick out the person who decreases R squared the least, or the next least value, okay? If the change in R squared does significantly change, we keep if it doesn't change, we keep kicking variables out. If it does significantly change, then we keep that variable in the equation, at which the process would stop, okay? So it's just the opposite of forward elimination, which again is not confusing at all, okay? The last method that we would use is a stepwise method, which not the most reliable method, just because there's a lot more chance for error, and usually you need a larger sample size. So sometimes if you see stepwise regressions, you'll see them in epidemiological studies where there's a lot and a lot and a lot of people involved. It follows the same procedure as forward selection, as in you start the regression model with no variables in it, but instead of being only limited to adding variables into the model or removing variables, you can do both. So I know we're running out of time, but I'm almost done. So if you have to leave, it's okay. I won't be sad. I use the example of putting on clothes, where you say, which article of clothing is going to cover the most of my body, right? Or which article of clothing is going to increase R squared the most, R squared being how much of my body is covered, okay? So I might say, I think pants cover the most surface area. So I add pants as a variable into my regression model. But then I'm like, oh crap, wait, underwear are also important. So then I can remove the pants, put the underwear in the model, and then put the pants back in the model, okay? So we have this option of adding in and taking away. to build our equation. Those are the four different methods. So enter or hierarchical, forward selection, backward elimination, and stepwise. Special notes to consider. We can still calculate standard error and confidence intervals for each of our coefficients. So that doesn't really change compared to bivariate. You'll just get a list of all of those values when you get your output in SPSS. Like I said, regressions are going to be strengthened with a larger sample size. And that's why I said usually stepwise regressions aren't really seen in a lot of research, especially if you have a sample size less than 40. So ideally you want 20 people per variable if you're running a regression to make sure that you have sufficient data to predict or to make a model that will predict a certain dependent variable. And then the last thing we want to make sure is that we cross-validate the equations. So I mentioned this before, you can have another set of sample data, and you can say, these are the observed values that we've gotten for some dependent variable. And I want to see how well does my model predict this dependent variable based on other measurements that have been taken that are in the model. So we do an example of that in the activity this week. The rest of the slides that are in the PowerPoint, I can skip through pretty quickly. It just tells you how to read or what components are important in the outputs that you'll get. So R, big R or little r, they virtually mean the same thing. This is the strength of the relationship between some variable. R square is going to be our covariance. This is actually a snapshot from the layered statistics page. So in our examples in class, our outputs will be extended over here, which is why I put this R squared change statistics. And those will tell you if R squared is changing significantly or not. So JT, you asked the question originally, what's the significance of R squared? That's where this comes in. But I go through examples of that in the flowchart video, and I think I show you guys as well in the activity video. I can't remember because I made it last year. But those are two things that'll pop up in the model summary part of the output. Another important part of the output that we don't pay much mind to in this class is the ANOVA table. And the reason why I skip over this is because we don't get to ANOVA tables until 2 weeks from now. So I just think it's like too much to introduce at one time. But there is a p-value for the entire model that just tells you the significance of the model and how well it actually worked within the given like sample data that you have. And then the last table within your output that you would be concerned with is the coefficients table. And this gives you your B values. Okay, so remember I said constant, that's B sub 0. So this should always be in your regression equation. And then the model that you end up choosing that has the largest R squared value is going to include all of these variables. So I go over examples of how you would actually build this equation where we have some constant plus B sub 1 times some X variable for age, right, plus whatever B sub 2 is, times whatever X variable there is for weight, plus B sub 3 times X for heart rate, right? And we can just build the equation that I gave you several slides ago. So that's B. Remember that earlier when we talked about bivariate regressions, you could calculate a t-statistic. So remember we can calculate t by dividing B divided by the standard error. SPSS has doesn't have rounding errors like we do, but if you did negative 0.165 divided by 0.063, you should get a value somewhere close to negative 2.633. Okay, and then t, this calculated t value is compared to some critical value, right? And then we can figure out, is that difference, right, between the sample slope and what we would expect in our population, is that difference significant or is it not, right? In which case we're saying, is some variable significantly contributing to our regression equation or is it not? Within the model that you end up with for your regression, all of these values should always be significant if you're doing a forward or a backward method. Same thing with stepwise, but I've never worked with stepwise. If you're doing an enter method, the significant level or the p-values might not always be, they might not always be less than the alpha that you've set. So that's just because you chose to put those things in there, or I told you to, okay? But remember, sig is just representing p. And then last thing, testing for outliers. We'll do some examples of this in the activity this week, so I won't spend too much time on this because otherwise it's just numbers. But we're bringing back quartiles in the interquartile range, which you guys already know how to calculate. And we can figure out where outliers exist in our distribution by using these two equations. So using quartile 1, we can identify the lower bound of where outliers would exist. Q3, we can figure out upper bound for where outliers would exist. It doesn't work on all outliers, so usually there's an additional method called the distribution of residuals. These are definitely not an exhaustive list of outlier tests, but they're the ones that the book comments on. So this distribution of residuals could often be used for regression specifically, because residuals are the distance between some point and the line of best fit. So that could also be used. We will use the box and whisker plot IQR method for this class. And that is all I have. So with that, are there any questions? I have fried your brains. It is okay. All right. I'm going to stop recording.